Hi all. Today we are going to discuss about one of the basic concepts in physics, that is scalars and vectors. Already in your previous classes you might have studied the fundamentals of what is a scalar and a vector. Today we are going to see more detailed study of scalars and vectors. So what is a scalar quantity? What you see is an example of a scalar quantity. A scalar quantity is a physical quantity that has only magnitude and no direction. Magnitude means a value. It will not have any direction. We will just say the length of the car is this much. We won't say towards the right or towards the left. So such quantities which is completely described just using a value is called a scalar quantity. Some examples of scalar quantities. So what you see in the table are all examples of different type of scalar quantities that you are going to study in this 2-year syllabus. Now, what are vector quantities? For example, if you want to describe the displacement between 2 points, always you have to specify the direction, like this example. So there will be a physical quantity and there is a magnitude and there is a direction. Then we call it a vector quantity. So a vector quantity is a quantity which has both magnitude as well as direction. A vector quantity is completely described only if you specify its direction. See some examples of vector quantities which you are going to study in your 2-year A-level syllabus. One of the problem with the vector quantities is their addition and subtraction. Since they have a direction, sometimes it will become a little difficult to add or subtract vectors. So let's see some simple examples at the beginning. A person is pushing and another person is pulling a table. A person is pushing with 4 Newton, the person is pulling with 3 Newton. So the total force acting on the table is what you call the resultant force, and in this example the resultant force is 3 plus 4 is 7 Newton, and here Newton is the unit of force and force is a vector. So you have to specify the direction. The direction is given as to the left. Here this is a very simple case because both of the vectors are acting along the same line and also in the same direction. So in this case it's very easy to add vectors even if the forces are acting from opposite directions but exactly in the same line, like the second example you see. So one person is pulling with 4 Newton, another person pulling with 3 Newton. What is the resultant force on the person standing in the middle? Here also you can directly subtract because they are exactly opposite to each other. So I'm subtracting bigger force minus the smaller force, and I have to always put the direction as that of the bigger force. Like this, if the forces or if the vectors are acting in the same line, either in the same direction or opposite direction, it's very easy to add or subtract. But what if the forces are not in the same line? So how do we add or subtract vectors if they are not acting in the same line? Let's see how to add two vectors if they are not exactly in the same line. For the simple case, let's consider how to add the vectors if they are perpendicular to each other or 90 degree to each other. You can consider the motion of a body. It's going from A to B, then B to C. Let's take A to B distance is 3 meter and B to C is 4 meter. The total distance traveled by the body. Remember, distance is a scalar quantity. So you don't have to care whether it has moved towards the east or north. You just need to add the values. 3 plus 4, you get 7 meter. But what is the total displacement? In order to find the displacement, you need to consider the directions. So the easiest way to find the displacement of any object is consider the initial point like A here, then consider the final point, that's C. Draw a straight line between initial and final points. Draw a line from A to C. This is how you represent the displacement of the object. But how do you calculate the value of the displacement, the magnitude? We know the direction now, but how do we find the magnitude? In order to find the magnitude of a resultant vector, we use triangle law. So let's see what does the triangle law says. It says if you could represent any two vectors like two sides of a triangle. For example, the body was going from A to B, then B to C. Let's consider the displacement from A to B like this, the 3 meter. Then it's going from B to C, it's 4 meter. If you could represent any two vectors like this, like the sides of a triangle, taken in order, that means the arrows should be continuous. The head of one arrow should touch the tail of the other one. That's what it means by taken in order. If you could somehow represent the vectors like this, then the law says the resultant will be shown by the third side. So the resultant will be shown by the third side taken in the opposite order. You can see the arrows. So for the green and the blue one, the arrows are continuous. You can imagine like clockwise. It's going clockwise. But the red one, which is the resultant, it's like anti-clockwise. So the resultant arrow should be always in the opposite direction of the other two vectors. That's how you represent the resultant of a vector. You calculate. Then even you can find the direction. Direction is usually expressed in terms of angle. How much angle it is away from the horizontal line or vertical line. So now let's see, if you could represent like this, how do you find the value of the resultant? It will be very easy if the vectors form a right triangle. Means if the angle is 90 degree. Here the angle between the 3 meter and 4 meter is 90 degree. That makes this situation simple. If your vectors form a right triangle like this, what you have just got now, then it is really simple to calculate the magnitude and direction of the resultant, because the magnitude of the hypotenuse always you can calculate using Pythagoras theorem. So if you apply the Pythagoras theorem here to find the resultant r, the equation goes like this: r square equal to 3 square plus 4 square, or r is equal to root of 3 square plus 4 square, which will give you the answer 5 meters. 5 meter is the resultant of 3 meter and 4 meter. That's a value. The value of the resultant is always obtained using Pythagoras theorem. Now, how do we find the direction? Again, I am using another rule from trigonometry, which is usually called Staccato. Okay, that means sine is opposite hypotenuse, cos adjacent hypotenuse, tan opposite adjacent. That short form is called Staccato. Let's apply Staccato here. I am taking tan theta, which is opposite over adjacent. Here the opposite of the angle theta is 4 meter and the adjacent side is 3 meter. That's what I have taken 4 by 3. Or you will get tan theta is equal to 4 by 3, or theta is equal to tan inverse. You can do it in your calculator, tan inverse 4 by 3, and you get 53.1. That is the direction of our resultant vector. There are many ways you can express this direction. The simplest way is you can say 53.1 degree with the horizontal. Horizontal is an imaginary horizontal line. Or even you can subtract from 90 degree and express with the vertical. Even you can say from east. You can see the red line is going from east towards north. It has already moved 53.1 degree from east towards north. That way you can express. Even you can express as the bearing. It is at a bearing of 36.9. Bearing is always explained from the north direction, how much angle it is situated now. That is what you call bearing, but it's not very commonly used in physics. Still, you could use any of these three forms, three ways to express your answer. Either you can write with horizontal, or you can write with vertical. That is just subtracting 90 minus, you will get with vertical. Or you can express the exact direction from the east, how much it has moved while it was going towards the north. Or even explain in terms of bearing. Okay, so we have found the magnitude and direction of the resultant vector. In the previous example, what we have seen, the two vectors were continuous, means they were head to tail. So directly we can apply our triangle law. But what if the vectors are not continuous? For example, a body is acted upon by two forces like this. Here the problem is the vectors are not continuous and our law needs the vectors to be continuous. For example, if I draw the resultant like this, I'm just completing the third side of the triangle. Is it correct? No, it's not correct because the other two vectors, 5 Newton and 7 Newton, are not in order, are not continuous. They are not head to tail. Our rule, the triangular law, needs the vectors to be continuous. So what we will do in such situations? Let's see how can we find the resultant of these two. What you can do is you can move any vector you want to any place unless you don't change the direction and the magnitude. So you can draw the 7 Newton or 5 Newton anywhere you want on this page, but you should not change the length or the direction of the vector. So let's say for the first example I'm moving 7 Newton. So let's see how can I move the 7 Newton so that the two vectors will become continuous head to tail. This is how I am moving the 7 Newton. Now you can see both vectors are continuous. Then if I draw the third side, here it's the hypotenuse, then you will get the correct resultant. So what you did is just made the sides like continuous or head to tail. Then you can calculate the magnitude using Pythagoras theorem. You will get the magnitude of the resultant, that is 8.6. So the magnitude of the red colored resultant is 8.6. Now you will be even asked to find the direction. Even if it's not asked, you are supposed to give, because all vectors are completely described only with magnitude and direction. Direction we are using always Occato. I'm using tan theta because 7 and 5 are the given vectors, and I will get the angle 54.5 degree with the horizontal, or from east 54.5 degree towards the north. This is one method. But you may be thinking now, what if we move the 5 Newton? Yes, it's possible. You can even move the 5 Newton. So let's consider the question again. This is a situation. The vectors are not continuous. I'm going to make them continuous. So this time I'm going to move the 5 Newton. See how I'm moving the 5 Newton so that the vectors are continuous. Now you see again the vectors are continuous. So you could move any vector you want. Then when you draw the third side, yeah, this is the result and it's correct. The magnitude will not change whether you move the 5 Newton or 7 Newton. The only difference that may appear is, in the previous example, we got the angle with the horizontal 54.5 degree. But now directly we won't get that angle. The angle what we get directly will be with the vertical. But it doesn't matter, when you do 90 minus answer you will get with the horizontal also. So let's see how to find this angle. Same rule, tan theta, but this time 5 Newton is the opposite. Okay, 7 is the adjacent. Then I got 35.5. And this angle is with the vertical. Before we got with the horizontal, now we get with the vertical. But it won't make any difference. When you do 90 minus previous answer, you will get this answer. So this is how you make the vectors continuous or head to tail or in order. Okay. With respect to the previous examples, let's see how to draw the vector diagrams, the different methods you can draw the vectors. Let's see, this is the first method. I'm drawing the horizontal vector first, then I'm drawing the vertical vector continuous to it, head to tail. Then I join them and get the resultant. This is one method, and the angle what you get in this method will be the angle to the horizontal. So I have drawn the horizontal vector first and I got the angle to the horizontal directly. Like that, if you want angle to the vertical, you can always draw the vertical vector first. Then continuously head to tail, you can join the horizontal vector. In this case, when you find the resultant, directly what you get will be angle to the vertical. These two ways you can easily calculate the resultant because both of them are triangles and you can use Pythagoras theorem or Socrates. There's a third way of representing the vectors like this, not continuous. In this case, the resultant should be drawn in the middle, just like that. The problem with this method is you cannot use directly for calculations, but this is also a method of representing all the vectors together. The first two methods we are using for calculation, but the last method also we use to represent the vectors. All the previous examples we have seen how to add two vectors. Now we are going to see how to subtract two vectors. Let's see this example. A body is going from A to B at a speed of 3 meter per second, then B to C at a speed of 4 meter per second. We are asked to calculate the change in velocity. It's not change in speed. Speed means directly you can subtract 4 minus 3, you get 1 meter per second as the answer. But the question says change in velocity. Change in velocity is always calculated as v2 minus v1, final velocity minus initial. But velocity has got directions. Directly you can't subtract 4 minus 3 because they are in different directions. Okay, so let's see how to solve it using the vector diagram. Let's draw the vectors. v2 is 4, then v1 is 3. I have drawn both vectors of my velocity v2 and v1 exactly in the direction shown in the question. If you directly join like this, if you directly apply the triangle law of vector addition, what you get will be v2 plus v1. We will get addition, not subtraction. So directly you can't join the vectors like this, and we have no rule to subtract two vectors. So let's see what to do. What I'm doing is the subtraction what you see in the equation, I'm going to make it as an addition. Let's see how to make the change. Instead of doing v2 minus v1, I'm writing v2 plus, what should I write? v2 plus minus v1. It's exactly same as v2 minus v1. The meaning of the second equation is if you add the vectors v2 and the vector minus v1, not v1 minus v1, then you will get your answer. So let's see how to do it in the vector diagram. Already v2 is there 4 meter per second. I don't have to change v2 because our equation says it's just v2. But v1 I have to change to minus v1. So let's see how to change v1 to minus v1. The only thing you have to do is just invert or just draw exactly opposite direction like this. That's minus v1. You have changed the direction exactly to opposite, so it will become a negative vector. Now they are not exactly like the sides of a right triangle, so I am drawing the minus v1 to this position so that now it will look like the sides of a right triangle, so that I can draw the hypotenuse and I can calculate the resultant delta v. So delta v will be equal to root of 3 square plus 4 square or minus 3 square plus 4 square. You will get the same answer. The answer will be exactly same as addition. The only difference comes in the angle. Okay, angle you can calculate tan inverse 3 by 4. Just take the magnitude and you will get 36.9. So So this is how you subtract two vectors. It's exactly same as addition, but one of the vector you have to invert. You have to take negative of the vector, then add. Okay. All the previous examples we were discussing cases where the vectors are exactly at 90 degree, so that easily you can make a right triangle using the vectors and their resultant, and you could apply Pythagoras theorem and Staccato. But what if the angle is not 90 degree? What if the vectors are not perpendicular to each other? How do we solve? Because the Pythagoras theorem applies only for right triangles. Let's see this example. You have a 3 meter and a 4 meter, just like the previous example, but they are not perpendicular. They are at an angle of 40 degree. Or this example, two vectors 4 meter, 3 meter at an angle of 120 degree. So how do we find the resultant of these two? Because you cannot directly apply the triangle law because the vectors are not 90 degree. Actually, there are two methods to solve this. The first method is using a graph or a grid or a space to draw. The second method is using the vector splitting or vector resolution. We are going to discuss both methods in detail. We are going to see an example how to find the resultant of two vectors if they are not exactly perpendicular to each other. Consider this example. A student is rowing a boat at a particular direction with a particular velocity, but the river is flowing with a current in another direction. So what will be his resultant velocity? Let's consider some values. The speed with which the student is rowing the boat is 1.5 and the direction is 65 degree to the horizontal. River bank means it will be horizontal, with the horizontal. And the current, water current is horizontal and 1.1 meter per second. So you can mark the vectors like this. The direction of his velocity and the river velocity are drawn there. And also you are provided with a graph paper. We are going to draw on a graph paper, then find the resultant velocity. Now let's see how to plot these two vectors on a graph paper and find the resultant. For your reference, I have written the velocities there. 1.5 and 1.1 are the velocities of the student and the river. I'm going to plot both these velocities on the graph. For that, first you have to choose a perfect scale. You have to choose a scale in such a way that your plot completes or covers more than 80% of the graph paper. In that way, you have to choose the scale. So depending on the size of the graph paper, you have to choose the scale. Here I have chosen 5 centimeter of the graph paper is equivalent to 1 meter per second speed. Let's see how to plot the vectors on the graph paper. I am using a protractor to plot in the exact angle. So in the question it's given the person is rowing the boat at an angle of 65 degree and with a velocity of 1.5. So I am cross multiplying. 1.5 meter per second is how many centimeters on the graph. You can use the scale to cross multiply, then you will get 7.5 centimeters. So I am drawing a line of 7.5 centimeter long and also at an angle of 65 degree to the horizontal line. That's my first vector. Now I want to represent the speed of the river current. I am using triangular law, so I am drawing continuously. Means the head of one vector is touching the tail of the other one. The second vector should be 1.1 meter per second. According to the graph, it should have a length of 5.5 centimeter. That's obtained by cross multiplying. Okay, 1 meter per second is 5 centimeter. So I have represented both my vectors in the exact magnitude and direction. Now I have to find the resultant. You will get the resultant just by joining the ends of the vectors. This is the resultant. Now we want to find the magnitude as well as direction of the resultant. The magnitude is the value. Directly you can keep a ruler and measure the length. So the length what I got is 11 centimeter. But remember it's not equal to 11 meter per second because we have a scale. So what I'm doing is I'm cross multiplying with the scale. 5 centimeter is 1 meter per second means 11 centimeter is how much? X I put, when you cross multiply you get 2.2 meter per second. So that is the resultant of the two velocities. The person will appear to move at 2.2 meter per second if you observe him from the seashore, okay, or river bank. Now it's not finished. We have to find the direction also. Because it's a vector, it will have both magnitude and direction. I am planning to find the direction with the horizontal like I marked in the red color there. That theta I want to find. Again I am using the protractor and measuring the angle, and the angle I got is 38 degree. So that's my resultant, and that's the angle of the resultant with the horizontal. This is how you calculate the resultant and angle using a graph. So no calculation, just measurement. Okay. Now let's see how you can do the same thing, finding resultant using a graph using parallelogram law. Previously what we did is called the triangular law. Now I'm going to use the parallelogram law. The method is very similar. You have to draw the vectors with correct length and angle using a ruler and protractor. The difference is instead of plotting the second vector continuously, that is head to tail, what I am doing is I am going to plot the vector on the top. So this is my second vector. Now what I am doing is I am going to draw two parallel lines which are exactly parallel and with the same length as these two vectors. For example, for the green one, this is the line which is parallel and it's having exactly same length. I'm going to repeat the same thing for the blue line and I get a parallelogram. Now just draw the diagonal of the parallelogram, you get the resultant. Then using a ruler you can measure the length of the diagonal and you can convert it to the actual value using the scale of the graph. So these are the two methods you can use to find the resultant of a vector using graphs. Okay, the parallelogram law and the triangular law on the graph. But what if no graph paper is given? So let's see the next method where we won't be given a graph paper and you have to find the resultant of two vectors which are not perpendicular to each other. Okay, this method of finding the resultant involves some process called resolving or splitting of vectors. You can split any vector you want, but you have to follow some rules when you resolve any vector. Let's see what are the rules. The first rule is any vector can be split but should have only two components. You can split a vector only to two parts, not more than that. The second condition is the parts or the components should be on either side of the original. You can imagine like a parent and kids. So kids should be on either side of the parent. Then you should start drawing the components from the base of the original or the parent vector. The next condition is the two components, the two kids should make an angle of 90 degree between them. They should be always perpendicular to each other, the components. Then no vector can have a component perpendicular to it. If you try to resolve anything 90 degree, it will go to 0. The value will be 0. Let's see what's the meaning of these statements using diagram. Okay, I'm going to explain all the rules whatever we have seen just now using the example of this particular vector A, which is at an angle of theta degree with the horizontal. I want to split this vector into components. The first rule says you can have only two components. So let's see how to split. For the simple case, I want one component to be in the horizontal direction. So I'm drawing exactly a vector in the horizontal direction. Now, the next component, the second component, the rule says it should be on the other side of the parent vector A and it should be exactly 90 degree to the first component. So this is how I draw the second component. You can see both components are exactly 90 degree to each other. The green and the blue components are perpendicular to each other. The parent vector A is gone. A is splitted into the green and the blue one. The effect of the parent vector A will be there in blue and green. Means if you combine them together, the green and the blue vectors, when you combine together, you will get A. So it's just like opposite of finding resultant. You can combine two vectors into the resultant means you should be able to do the reverse. You should be able to split a vector into two components. That's what we have done here. Let's name the component as x and y. Now we are going to find the values of this component. Since I have split it horizontally, I can call it horizontal component, the other one vertical component. There is no rule like you have to split into horizontal and vertical. You can split in any direction you want, but the angle between the components should be 90 degree. Okay. So let's see how to calculate a value for this x and y. Compared to the parent vector A, how much will be the value of y, how much will be x. In order to find that, I am making a triangle with all these vectors. For that, the vector y I am drawing here. It's the same thing, I just replace the vector to this side. It won't make any difference, but I get a triangle so that I can apply Staccato. Cos theta will be adjacent by hypotenuse. Adjacent side is our vector x or the x component. Or when you cross multiply, you get the value of x. X will be always a into cos theta. The original, the parent vector into cos theta. Now in order to find y, I am using sin theta because y is in the opposite of the angle. So sin theta will be opposite over the original hypotenuse, that's the original vector a, and you get y is equal to a sin theta. This is how you find the value of components. But every time drawing a triangle and finding the value will be very difficult. So what you can remember by heart is the component which is touching the angle. Like you can see the component x, the horizontal component is touching the angle theta. The component which touches the angle will be always the cos component, like a cos theta. And the component which is not touching the angle, you can see the vertical component has no direct contact with the angle. Such components which are far away from the angle or no direct contact with the angle will be always the sine component, like a sine theta, where a is the parent or original vector. So always you can name the component as a cos theta and a sine theta, where a is the name of the parent vector or the original vector. Let's see another example. So you are given a vector, 10 Newton is the magnitude of the vector, and a and b are two components. Means I have splitted the 10 Newton into two parts, a and b. We are going to calculate the value of a and b. So first thing you have to notice is which component is touching the angle. That will be cos component. Here the vector b is the one touching the angle 30. So the value of b will be 10, that's a parent vector, into cos 30 or cos theta. Okay? Like that, the vector a is not touching the angle. So the value of vector a should be 10 sine 30, which is 5 Newton. So this is how you find the value directly. The component which touching the angle will be always cos component, and the component which is not touching will be always sine component. So here the example I have taken is 30 degree, but what if the theta is 90 degree? Means you are trying to split a vector with a component 90 degree perpendicular to it. So let's see what will happen if you try to split a vector 90 degree to it. For this you need to know the values of sine theta and cos theta, at least the extreme values, like sine 0 is always 0 and sine 90 is 1. cos 0 is 1 and cos 90 is 0. So sin theta and cos theta are always opposite to each other in values. From the values, what you can see is as you increase the value of theta from 0 to 90, the sin theta value is increasing from 0 to 1. So as theta increases, always sin theta answer will increase. At the same time, when theta increases from 0 to 90, the cos theta values is decreasing from 1 to 0. So sin theta always increases with theta and cos theta always decreases with theta. Now let's take this example. There's a 10 Newton and I want to split it to two components which are perpendicular. So I am splitting one component 30 degree. Obviously the other component should be at 60 degree because the total should be 90. So let's calculate the values of this component using 10 cos theta for the blue one and 10 sin theta for the green one. You will get these answers. Okay. The blue component was 8.7 and the other one is 5 Newton. Now I am increasing the value of the angle. Just to want to know what will happen as the angle increases. So I am making now 45 degree. Both components are exactly at 45 degree because the total angle between them should be 90 degree. So let's calculate the value. You can see the cos component value now is 7.1 and sin also 7.1 because both are 45 degree. What you can see is the sin component value has increased and the cos component value has decreased because the angle is increasing. Okay. Now let's take a bigger angle. Let's take 60 degree. Now let's again calculate 10 cos 60 and 10 sin 60. You can see the cos value again decreased and sin value again increased. So as you increase the value of theta, the sin component will always increase. It will become bigger and bigger. You can see it has grown. It has grown very similar to the parent, but the cos component has shrinked or it has become less magnitude and it is very much small compared to the parent now. Now let's take what will happen if the angle is 90 degree. I'm going to calculate 10 cos 90. 10 cos 90 is 0. Means you cannot have any component 90 degree to a vector. Or if you try to split a component 90 degree, the value of the component will become 0. Okay. So this is a very important rule. In a general way, you can say no force, no vector will have an influence perpendicular to it. That's the meaning. For example, our weight. Our weight is vertically downwards. Our weight has no influence in the horizontal direction. If it had some influence in the horizontal direction, we would be always accelerating horizontally. So that's an example of why no vector can have a component perpendicular to it. Okay. So any component 90 degree will have 0 magnitude. This is a very important rule in vector resolution. Now let's see how the splitting or resolving a vector will help us to find the resultant. If you consider this example, 3 Newton and 4 Newton are force acting on a body at an angle 40 degree to each other. We can solve this case if you are given a graph paper or a grid, but we are not given a graph or grid. We are going to solve this using calculation or using the splitting of vectors. You can split 3 or 4. Any vector you can split in any way you want. But always keep in mind the reason for splitting. What is our aim? Here the aim is to make the vectors either same line or perpendicular. So always keep in mind that we are going to make the vectors either in the same straight line or perpendicular to each other. For the simple case, I am splitting 4 Newton. So 4 Newton I am going to split into two parts. One component I am splitting exactly parallel to the 3 Newton. So the brown colored vector is the horizontal component of 4 Newton. I want one component in that direction because I can add with the 3 Newton. 3 Newton was already there. I'm not touching it. Now the 4 Newton, one component you have drawn exactly parallel to 3 Newton so that you can add both. Where will be the other component? Our rule says the other component should be perpendicular to this one and should be on the other side of 4 Newton. So let's see how the other component will come. This is the other component of 4 Newton. Now the 4 Newton is gone. Then we have two components. Now we are going to name it. The component which touches the angle. Here 40 degrees is the given angle and the brown colored component is touching the angle, and that is 4 cos 40. 4 is the original or parent vector, and cos 40 because that component is the one touching the angle 40. The violet colored component which is not touching the angle should be 4 sin 40 because not touching is always sine. The 4 Newton is gone. We have only two components, 4 sin 40 and 4 cos 40. Now the situation looks very simple because two vectors are already in the same direction and one vector is perpendicular. So I'm going to solve the same direction once. I'm going to calculate 4 cos 40 and 4 sin 40. Now you can directly add 3 Newton and 3.1 because they are in the same direction. So you get a single vector with a value 6.1 and the other one is 2.57, which is exactly perpendicular. Now it's look like very simple case and you just need to arrange them continuously to apply the triangle law. Then draw the resultant in the opposite direction, that is tail to head. Then you get the resultant of these two vectors and even you can find the angle. The resultant value, as you know, always found using Pythagoras. So you can apply Pythagoras theorem just like we did before and you can find the resultant. Even the direction or the angle you can find using Socrates. I'm using tan theta because the two given vectors are like that. I get 22.8 degree. To be specific, I have to say 22.8 with horizontal because the angle I have drawn there is with the horizontal. Now let's take a little more complicated case. Here the angle between the two forces are 120 degree. Let's see how the splitting of vector will help us to find the resultant of these two forces. Directly we can't find because they are not same line, they are not opposite, or they are not even perpendicular. So let's split the 4 Newton, but as I told you can split even 3 Newton also. So you can try that way also. I am here splitting the 4 Newton. One part of 4 Newton I am splitting exactly opposite to 3 Newton so that I can later subtract them or solve them very easily. So always keep in mind the reason why you are splitting. Okay, so one component is there, the other component should be on the other side of 4 Newton and exactly perpendicular to the first component. So these are the two components, the brown and the violet ones are the components of 4 Newton and 4 Newton is gone. Now the problem is finding the exact angle. The total angle is given as 120, but I need to find the angle with the violet colored component and the original vector. But you can see the violet colored component is perpendicular to the green one. So that angle will go as 90 degree. Then the total angle was given 120. So the remaining is 30. That is 120 minus 90. So this is the angle. Now we can name the component. Touching the angle is cos, not touching the angle is sine with the parent name at the beginning. The original vector name is 4. Okay, so these are the vectors. 4 Newton is gone. Now it's simple because you have only 3 vectors, 2 of them are already opposite to each other and the third one is perpendicular. First I am finding the value of 4 sin 30. Sin 30 is half, so you get 2 Newton, and 4 cos 30 is 3.46 Newton. 2 Newton and 3 Newton are exactly opposite, so I can directly subtract them. I get a single vector of value 1 Newton. Now it looks like the triangular law. What you need to know is just move one vector. Any vector you can move, but here I am moving 1 Newton in such a way that the vectors look like continuous. Then draw the resultant in the opposite direction and you get the resultant, and even the angle you can calculate. Okay, so the resultant value is always found using Pythagoras theorem, and the angle is found using Stoccato. But this time the angle you will get with the vertical line, okay, or with the violet colored vector. Okay, so it's not perfectly vertical, so you can say with the vertical violet colored vector. Okay, let's do some calculations involving resolving of vectors. It's an important situation in physics, what you call an inclined plane. A body is moving down through an inclined plane. The two forces acting on the body are its weight and the normal contact force or normal reaction or the push from the plane. Now, the question is, what will be the component of normal contact force along the plane? Means along the direction of the plane, if you split a component for r, what will be the value? The component what they are talking about is the one which is represented by dotted line. So if you try to resolve any vector 90 degree, the component value is going to be 0 because cos 90 is 0. So the answer is 0. Normal contact force R cannot have any component along the plane. Now let's see the same situation with another example. This time the inclined angle is given. The plane is inclined at angle 30 degree to the horizontal. The question is to find the component of weight along the plane, and the options are given. Previously we found the component of normal contact force along the plane and we got 0 because normal contact force is exactly perpendicular to the plane. But in the case of weight, it is not perpendicular to the plane. So weight will have a component along the plane. I am going to draw that component. This red colored vector is the component of weight along the plane. Weight will have another component on the other side of it because every vector should be having two components. This is the other component of weight, and the red and the green component should be making an angle of 90 degree between them. They should be always perpendicular. Now I have got the component, now I need to find the values. Which one will be mg cos 30, which one will be mg sin 30, because 30 is the given angle. Let's find it. In order to find that, you need the angle at the base of the vectors, the starting point of the vectors. So I'm going to find the angle at the base of the vectors. For that, first I can consider a triangle with the total angle 180 degree. So 30 degrees there, then this is 90 degree. You can see directly from the diagram it's 90 degree. Then the third angle should be 60 degree. So that the total you will get 180 degree. Again, the two components, the red and the green one, should be 90 degree to each other. So if the given angle there is 60 degree, the other angle should be 30 degree. So this way you can easily remember what will be the angles. Okay. Then now we are going to name the components. The component which is touching the angle 30 degree is always the cos component. So the green is mg cos 30. There should be mg always, that's a parent. So the parent name should be there before cos or sin theta. Then the other component which is far away from the angle, which is not touching the angle, should be the sin component with the parent name mg sin 30. These are the components of mg along the plane and perpendicular to the plane. So the component of mg along the plane, our answer is mg sin 30. Let's see some of the real life applications of the splitting of vectors. I'm going to consider the same example what we did before, but using a graph. This time no graph is given. We are going to use the splitting or resolution of vectors to solve this problem. This was the question. The person was having a velocity 1.5 meter per second at 65 degree, but the river current is 1.1 meter per second horizontal. What is the resultant velocity? If you are looking from the river shore, how much velocity that person will be appearing to you? That's a question. So let's use the idea of resolving the vectors to find the resultant velocity of the person. So I am drawing both vectors. 1.5 meter per second is the speed of the student and 1.1 is the speed of water. Now the problem here is the vectors are not perpendicular to each other. So you cannot directly use the right triangle or Pythagoras theorem to find the resultant. Pythagoras theorem applicable only to 90-degree or perpendicular vectors. In such situations where you see the vectors are not already perpendicular to each other, you have to resolve the vectors. If a graph is given, you can draw a vector diagram and find the resultant like we did before. But if there's no graph given, you have to go for vector resolution. So let's see how I am going to do this. I am going to split the 1.5 meter per second, which is not vertical or horizontal in this example. So I'm going to split it exactly one vertical part, and the other part should be horizontal because the components should make 90-degree to each other. The 1.1 meter per second is already there, but I'm not touching that. I have just splitted 1.5 into two parts. So the 1.5 is gone. Only the two parts, two components exist. The next step is finding the value of each component. How much is the value of the green one? How much is the value of the red component? The rule says touching the angle. Here the green colored vector is touching the angle. Should be cos component with the parent name. That's the original 1.5. So the green component value is 1.5 cos 65. 1.5 is the original vector and touching the angle should be cos 65, so you get 0.63. Now the value of the red one should be 1.5 sine 65 because it's not touching the angle. We have to consider it as sine component. These are the values of the components of 1.5. Now you can see that two vectors are exactly in the same line and they are exactly in the same direction, so you could directly add them. So I'm directly adding the two vectors and I get the total as 1.73. So I can represent total thing just by a single vector of 1.73. Always you can directly add the vectors if they are in the same direction, or you can subtract if they are exactly opposite to each other. You don't need any special rules. Now we got both vectors like sides of a right triangle. You fix the vectors in the correct position to make it a triangle. Remember, the vector should be continuous, head to tail. That's why I had to move the vector to this side. Now when you draw the third side, that's hypotenuse, you get the resultant. The value of the resultant you can find using Pythagoras, and the direction you can find using Zucato. Okay. Now let's see another example of splitting or resolving vectors, the hammock. You can see a student is lying down in a hammock which is suspended at an angle of 20 degree to the horizontal. The tension in each side of the rope is given as 500 Newton. You are asked to calculate the mass of the body. So to begin with, I'm going to draw all the forces acting on the person. Acting on the person. The first force is weight. Of course, weight will be there everywhere. Then the other forces are two tensions. The values are already given, it's 500 and the angle is 20. So I have drawn all the forces acting on the person. Now I am asked to find the weight. The two forces which are sort of going upwards I know, and I am asked to find the downward force. Can I tell W is equal to 2 times 500? That's 1000. No. Here we cannot say that because they are not in the same line. This is a situation where the resolving or splitting of vectors comes for our help. Let's draw the free body force diagram for the person. I'm going to draw all the forces acting on the person. That's the weight and the toe tension, 500 each, which is at an angle of 20 degree to the horizontal. So all the forces are marked there. The idea I'm going to use now is the total upward force should be equal to the total downward force since the body is in equilibrium. The person is not moving. So the upward force should be balanced by the downward force. But the problem is directly you can't equate W is equal to 500 plus 500 we can't write because the forces are not in the same line. In such situations we are going to split the vectors. So let's see how you can split the vectors. I'm going to split the 500 Newton on the left side first. So let's see how can you split that 500 Newton. So whenever you split, there should be two components, and the splitting of a force should be always useful. So here what I want is I want some force exactly opposite to the weight so that I can equate weight is equal to something. So keeping that in mind, I need something exactly opposite to weight. I am splitting the 500 Newton. So one component of 500 Newton I am splitting exactly opposite to weight. And of course there will be another component. There should be always two component. The other component should be on the other side of 500 Newton and also perpendicular to the first component. So the dark green and light green are the components of the 500 Newton tension which is on the left side. This is the first step. So I got something exactly opposite to weight so that I can equate. But I need to find the values of each component. In order to find the values, I need to get the angle at the base of the vector. So I'm using small mathematics here. I'm using the idea of z angle. So if you use the z angle idea, you can see the angle at the base becomes 20 degree. So according to our rule, touching the angle component should be cos component. That is t, that's the original vector, into cos theta. That's touching the angle. So you get 500 into cos 20, you can calculate that value. The component which is not touching should be t sine theta, where t is the parent vector, original vector. So these are the two components of 500, and the 500 is gone. We have only these two components. One exactly opposite to weight, other one perpendicular to weight. But still there's another 500. We have to think about every force. The law says total upward and total downward. So total means I have to consider every force. So I'm going to split again the next 500 on the right hand side. It's splitted one component exactly opposite to weight, other component perpendicular to it. So the dark blue and the light blue are the components of the 500 Newton on the right hand side. And again I'm using Z angle to get the angle at the base. And I can write this is 500 cos 20 because touching the angle should be cos component. And the dark blue component is 500 sin 20. So this is our situation. The both 500 has gone. We have only the components. So you can just remove the 500s and yeah, this is the picture. Now it's really easy because you see every force opposite to each other so that directly you can equate. Like W is exactly downward and we have got something exactly opposite to it, vertically upwards, that is 2 t sine theta components. There are two. So the total downward force W should be equal to total upward force t sine theta plus t sine theta. Or you can substitute the values 500 sine 20 plus 500 sine 20 and you get 342 Newton. That's the weight of the person. But the question asked the mass, so you could directly divide by 9.81 and you will get the mass. Okay, so this is how the splitting of vectors helping us in different situations. So whenever you feel like the forces are not in the same line, you can always split one of the forces, or you can even split all the forces if needed. Let's see another example. Two magnets are suspended as shown in the figure, but when you suspend two magnets like that with the like poles, like north and north, let's say facing each other, it won't stay there. It will just get repelled and move away like this. And at some point, it will get stopped when all the forces acting on them are balanced. Now we can say the magnets are in equilibrium. So the mass of the magnets are given, and at what angle they stay in equilibrium is also given, that 70 degree. The question is to calculate the magnetic repulsive force on each magnet. How much force each magnet experience. Anyway, the force experienced by each magnet should be exactly equal because of Newton's third law. The left magnets push the right one and the right magnet push the left one. Okay, now let's see how to calculate this force. The first step in solving any problem involving forces is to draw a free body force diagram. A free body force diagram will have all the forces acting on a particular body, but here there are two bodies, so I'm going to remove one of them. Now there's only one body. I'm going to draw all the forces acting on that body. Of course, there will be weight, and if it was only weight, it would go to the earth. So there is some force which preventing it from going downwards, and that's tension. Tension in the string will pull the body upwards. Again, if it was only tension and weight, it would stay vertical. But it's staying at an angle means there is some force which is pushing it towards the left side, and that's the force we are going to find. That's a magnetic repulsive force. So this is the situation. The value of weight is already given in the question. Tension we don't know, but we know the angle. The problem here is the forces are not in the same line. So you cannot directly add or subtract, or you cannot apply Pythagoras theorem or anything, since they are not exactly in line or they are not exactly perpendicular. Two forces are perpendicular, but the third one, tension, is not. So what I'm going to do is, the tension looks like odd. It's at an angle. So what I'm going to do is I'm going to split tension. I'm going to resolve tension in such a way that one component of tension comes exactly opposite of mg. Then automatically the other component will be exactly opposite of the magnetic force, because the two components should be 90 degree to each other. Now the tension is gone. Okay, we have only two components, one exactly opposite to mg, other one exactly opposite to the magnetic force. The second step now is to find the angle at the base. So again I'm using z angle, then I can get the angle at the base. The component which is touching the angle should be the cos component with the parent name tension, T cos 35, and the other component automatically will be T sin 35. This is the picture now. So what we have got is weight is equal to T cos 35, and in the horizontal direction the repulsive force, the magnetic force, is T sin 35. We have two equations. The problem here is we don't know tension. If we know tension, then directly you get the answer. With the first equation, you can directly get the answer if you know tension. But tension is not known. And the question doesn't say to calculate tension separately. So I'm going to do it directly without finding tension. You could even do after calculating tension, but there's an easy way without finding tension. So I'm going to divide what you call simultaneous equations. I'm going to divide one by one every term. So remember to write sine theta equation on the top always, so that when you divide you get sine theta by cos theta, you can get tan theta. So always remember to write the sine theta equation in the numerator. I'm going to divide the left hand side, r divided by mg. On the right hand side there are two tension, so they will just get cancelled. That's the advantage of doing simultaneous equations or dividing one equation by another equation. you can just cancel the unknown quantities. Now your answer becomes, the left hand side will be r by mg, and right hand side sin 35 by cos 35 becomes tan 35. I'm cross multiplying, r is equal to mg into tan 35. I know weight, because mass is given, multiply by 9.81 will give you the weight, and tan 35 you can calculate 0.7. Finally you will get the answer. The repulsive force is 0.1 Newton. Okay. Now let's see another repeated type of question, that is inclined planes. Let's see this question. A body is kept on an inclined plane. Let's see what happens when you keep a body on an inclined plane. It will accelerate downwards. So you are asked to find what is the resultant force acting on it which causes the acceleration. In order to find the resultant force, first you need to know what are the forces. The result of every force together is called the resultant force. So first of all, I'm going to find out what are the forces. For that, I need a free body force diagram. Just consider the object in the middle. Let's say they are reaching there, that point. I'm going to draw all the forces. And the most important and repeated force is weight. It comes everywhere. But if it was only weight acting on the body, it will fall right through the inclined plane. It will go to the earth. But it's not happening. So there's some other force which is preventing it from moving vertically downwards. That force is called the normal contact force or the normal reaction. The word normal means perpendicular. Means it should be perpendicular to the surface or 90 degree to the surface. These are the only two forces acting on the body, because it says frictionless plane. So these are the only two forces. And now I want to find the resultant force. You cannot directly subtract r minus mg or mg minus r because they are not in the same line. If they were in the same line, directly you can find the answer by subtraction, but here it's not possible. Now we are going to find the resultant force. So before going to calculate, you can have an idea which direction will be the resultant force. Since it's accelerating along the plane, the resultant force also should be along the plane, which is represented by the red colored vector. So that is the direction of resultant force. Now you can see which force, R or mg, can have a component like that. Which force will have an influence in that direction, or which force you can split along that direction. If you think about R, it's exactly 90 degree to that direction. Already we have seen no vector can be splitted perpendicular to it. Means R cannot have any component along the plane. So it's mg which creates that component, and due to that component only it's accelerating downwards. So let's split mg. One component already I have drawn there along the plane. Automatically the other component should be 90 degree to this component, and it will be exactly opposite to the normal contact force. These are the two components of mg. So mg is gone, and you have two pieces of mg. One is the red colored component, other one is the green colored component. Together it makes the mg. That's the first step. Now second step is finding the component values, which is cos, which is sine. In order to find that, you need the angle at the base. So you can always remember, if the inclined angle is 30, then the angle between that component and the weight will be also 30. Okay, so the component touching the angle should be mg, that's the original vector name, mg cos 30. And the component which is not touching along the plane is mg sin 30. So mg is gone, and it is replaced by its two components, mg cos 30 and mg sin 30. Now if you observe the situation, you have only three forces acting, and two of them are exactly opposite to each other, and they are equal to, because it's not going up or down, the body is not moving upwards or downwards, means the normal contact force and the mg cos 30 should be exactly equal, and they cancel each other. They just cancel, and the only thing remaining on the body is mg sine 30. Whenever you add and subtract every forces, and the only thing remaining on a body is called the resultant force. The resultant force in this case is mg into sine theta or sine 30. Mg is also given, angle also given. So the resultant force on the body is 10 Newton. Using this resultant force, even you can calculate the acceleration of the block also. Okay. Now let's see how to solve a problem using vector diagram. A boy is flying a kite, and we are going to draw all the forces acting on the kite. First of all, there will be weight, which is there on every body. Then there's a string, there's a stretching, so there will be a tension. And there should be a force which maintains the height or which pushes the kite upwards, which is called upthrust. Every object in the air will experience an upward push due to the air. That's called upthrust. Now you can see the kite is not exactly vertical, it's at an angle. So there should be some force towards the left side which keeps the kite in that position. That force is called drag force, or generally we call air resistance. These are the four forces acting on the kite. Okay, so these are the four forces acting on the kite. Now the question says to draw a vector diagram to show that the body is in equilibrium. Means by a suitable diagram we are going to show all the forces acting on the kite are balanced. Okay, let's see how to draw a diagram which shows equilibrium. So you have to draw all the forces, but you have to draw the forces in such a way that they are continuous. Means the head of one vector should be touching the tail of the other vector. So let's see how you can draw in a suitable way. So first I am drawing lift force there. Then in continuation, I am drawing the tension. So you can see the head of the lift force is touching the tail of tension. Okay. Now I am drawing the weight continuously. Then I am filling the gap with the drag force. That's the only thing left. So now what you see is a closed shape. Any closed shape will show the body is in equilibrium. And you can see all the forces are continuous, all the vectors are continuous. So if you get a closed shape and all the vectors in the shape are continuous, that means equilibrium. So that's the condition for equilibrium. So any situation where you are asked to prove the body is in equilibrium, you have to fit the vectors in the correct place so that you will get them continuous to each other, and also you will get a closed shape. This is what you mean by equilibrium. Now let's do a calculation for the same situation. So this is the question. You need to find the tension in the string. All the other forces are given, but tension is not given. So you are asked to calculate the tension. But the problem here is it's a trapezium, not a triangle. So directly you cannot apply Pythagoras theorem. So what I'm doing is I'm going to make this trapezium into a triangle. So what you can see is two forces are exactly opposite to each other, the lift and the weight. So easily you can solve lift and weight. Like you can subtract lift minus weight and you can get a single vector. Okay, the single green vector represents lift minus weight. Now it's a triangle, it's a right triangle, so you can easily apply Pythagoras theorem. The values are given, drag force is given as 6, then lift minus weight, when you calculate you will get 3.86. Now we are going to find tension. You can use Pythagoras. A square is equal to b square plus c square. Then tension you will get 7.1 Newton. That's the magnitude. But since it's a vector, you may need to find the direction also. Here I'm going to find the direction of tension with the horizontal. So I can imagine the angle at the bottom, and I'm going to find using Stoccato. So tan theta will be opposite. If you imagine the angle at the bottom, or the head of the tension. The opposite side is 3.86 and adjacent is 6, and you will get the angle as 32.8. So with this we will conclude the discussion on vectors, and thank you for watching this presentation. Thank you so much.